In the previous video, we talked about Davidson and Germer's experiment where they were looking at the diffraction of electrons. We're going to take that a little bit further in this particular video to help us explain this idea of Schrodinger's equation. And so first of all, thing to note here is that if you're looking at the idea of diffraction of electrons, it needs to be that the electrons are fired at a suitably narrow single slit. And when you do that, because you've got individual electrons that you're dealing with here, you need to allow this process to occur over time. So it can't just be sort of, you do it in a short period of time. You need to allow it to sort of develop over time. A diffraction pattern will appear, and or if diffraction pattern is observed, I should say. That sort of diffraction pattern that we're talking about here looks like this. So you can see on the left, it sort of there's all these electrons that are appearing, no real order to them. In the middle, at some later point in time, you can start to see that they've got these bands that are forming where we're seeing more electrons and sort of a little bit less in between them. And over a very long period of time, we start to see this very large density of electrons through the middle, and then a gap, and then another increase in intensity again. So again, that's similar to what we'd see for a diffraction pattern for light. Now the thing with electrons though is that we can't really, like, we're treating each electron as being a separate particle. So by seeing this pattern, it allows predictions to be made where electrons aren't going to appear, because we can see there that there are spots where electrons just don't end up appearing on the screen. So it allows those predictions to be made fairly easily, so where they will not reach. But for individual electrons, we can't really predict where they're going to appear. So we can't sort of fire a single electron and say, well, this is where we expect it to be, because it could be in any one of those regions. So for individual electrons, predictions are not possible. What we can do though is look at the fact that if we analyze the spread of electrons over time, we can consider that diffraction pattern as being a bit of a probability distribution, I guess. So the diffraction pattern itself, while it is an indication where the electrons have ended up, we can think of it as a probability function. So the probability of where electrons are going to fall, or of where electrons will reach. And so basically it means that if you look at this scenario, we'd count that there were more electrons in this middle region and then fewer electrons in this next region and fewer again. So if you think about the stereotypical graph for diffraction of light, where we see this sort of pattern occurring, we can use that as the probability function for where electrons are going to fall. So more of the electrons are going to fall in this central region and fewer on these secondary bands further out. Now, in order to sort of figure this out a little bit more, Schrodinger proposed that a wave function, so what we mean by a wave function is simply a function that describes the shape of the wave that corresponds to the particle. Now, the idea of what that wave function actually describes in terms of physical properties, it's still being debated today. Like, is it a single electron? Is it a group of electrons? So we don't really need to try and identify what the wave function is actually about. We just need to know that the wave function exists, and it describes the quantum state of the particles. and we'll see in a bit further that there's one particular aspect about that wave function that we're interested in, and that thing is that it's more about the amplitude. So it can be thought of as the amplitude of the de Broglie wavelength. So we've got this wave function. How do we relate that then to the interference pattern, or the diffraction pattern, I should say? I want to just refer back here to the idea of what we saw for the diffraction pattern for light. So for light, we're interested in the intensity of those bands. So we observe the intensity and not the amplitude of the light. But you can see there we're interested in the amplitude, given that we're dealing with the amplitude of the de Broglie wavelength. But what we do know is that intensity is proportional to this square of the amplitude. So we can take that idea of intensity being the square of the amplitude and apply that to the Schrodinger wave function and link it back then to the diffraction pattern. So combining those ideas, we basically then have this we're now looking at the fact that the greatest probability of finding an electron will be where the wave function is at a maximum. Now, given that the wave function could be both positive or have positive and negative values, we need to sort of remove these negatives, because negatives don't really have meaning in terms of probability. So we're going to take the magnitude of the wave function and square it. So where that magnitude, or the square of the wave function, square of the magnitude of the wave function is a maximum, that's where we're going to see the greatest probability of finding an electron. And sort of follows logically from that, where the square of the magnitude of the wave function is 0, there is 0 probability of finding an electron. So that then leads us to the idea now of the probability of finding an electron. So we're not actually talking about directly observing where the electron ends up. We're talking about the probability of finding electrons in certain regions. If we allow a lot of electrons to be diffracted. So the probability of finding a particle at a distance r, so think of that distance as being how far from the central bright region, and we're using that from a chosen reference point. And keep in mind here that the wave function depends on the particle that we're dealing with as well. So the probability then is given by the equation P representing probability at the distance r is going to be the square of the magnitude of the wave function multiplied by delta V, where delta V is the volume being considered. Now, the main thing to be aware of here, yes, you've got this equation where you can sort of look at probabilities and things. The main thing to be aware of is that when we're dealing with wave properties of things that we typically consider to be particles, we can't exactly tell where each individual particle is going to be, so we need to refer instead to a probability. Now, there's an interesting aspect here too. If we consider, say, interference of an electron travelling through two slits, we'd still see that same sort of wave property of interference occurring for an electron travelling through two slits. So the interpretation of that scenario then is that as the electron travels through the slits, where we imagine that it's the wave function means that it travels through both slits and then strikes the screen. It isn't until it strikes the screen and we make a measurement of it that we're then treating it as a particle. So in that situation, when you make that measurement, the wave function collapses and it sort of reverts back to classical physics, so treating the electron now as a particle. So basically the idea here is that if you measure something as a wave, or if you measure wave properties, then it acts like a wave. If you measure the particle properties, then it acts like a particle. So it depends on the measurement you're making as to whether the thing that you're measuring, whether you're going to see the wave properties or the particle properties. We'll have a bit more of a discussion about that in class to try and really help you wrap your mind around this idea of things being able to be both a wave and a particle at the same time.